Look at those good looking cats right there.
All right. All right. So, chapter 2. Chapter 2.
Chapter
So,
2, baby. Made it through chapter 1.
If you want to jot this down here, I'll kind of talk about this. Now, one of the things that we started with the very first day was this idea of instantaneous rate of change, right? That very first exploration about the door swinging open. At what rate was it opening? At 1 second was instantaneous rate of change. We've now come to know that that is the derivative, right? That is the slope at one point. That is the tangent line to the curve. We talked about letting those 2 points get really, we can't do slope with only 1 point. We need 2. So we talked about letting those 2 get really close together. And on the quiz, we even did that problem with the zooming. And we picked 2 points really close. And we did that. And we did that very first day. And then we contrast that to average rate of change. So on your homework today, you're going to have some problems that ask for the instantaneous rate of change, that ask for the derivative. Those 2 are the same thing. And then you're going to also have some problems where it's going to ask for the average rate of change. And when you hear average, don't think average like add them up and divide by how many there are. That's not the kind of average we talk about in calculus. The average that we do is the average, the word or the use of the word average that we will have most of the time is right there, average rate of change, which simply means slope between 2 points. It's the old algebra version of slope. Average rate of change. We simply subtract the y's, subtract the x's, which is what you did on that quiz question. You happened to pick 2 really close points, so what you did was average rate of change, but it was a really good approximation of instantaneous rate of change. Excuse me. because those 2 points are so close together, it's a really good approximation of instantaneous rate of change, but it's still average rate of change. If you do slope between 2 points, you're still doing average rate of change, okay? But if you pick those 2 points really close together, you're getting a good approximation of instantaneous rate of change. Now, the name we have for that is the difference quotient. The name for the slope formula is the difference quotient. You're subtracting and then dividing. Done. The difference quotient. Okay, so when you hear that phrase, the difference quotient, that's what we want to think of. The slope between 2 points formula. Okay? All right, so what chapter 2 is going to lead us into here is taking these ideas that we have developed in chapter 1, the whole chart and these interactions between f and f prime, and we're going to get more technical, and we're going to get more into using equations for it. Think about what we've done up to this point. It was all graphical, right? Everything were graphs on that last quiz. I gave you an f graph or an f prime graph or an f double prime graph, and we talked about f and f prime, f double prime. So we want to be able to do that. But we also now want to be able to do it when we are just talking about equations, right? If I give you an f equation and an f prime equation, f double prime equation, now you could always graph them and then do what we did in the last chapter. But what if you don't have a graph? What if you don't know what the graph looks like? What if the graph alone doesn't tell you? Because think about on the quiz, we had that one where we were just guessing that it landed at about 5.5, or the one where I had to tell you that it crossed at 0.56 and at 0.72. Where do those numbers come from? So we're going to want to use equations. We're going to want to be more specific and more exact. So that's where we're headed today. So same ideas, okay, but we're going to dive into them here in using more of equations and that kind of stuff. Now, for today, we won't get too much into equations of the functions. I mean, we'll be using some equations, but we will still be doing some calculator stuff, some calculator values, finding, plugging in and so forth, those kind of things. All right, so we do have something we're going to add down here under instantaneous rate of change And we're going to come back to that in a little bit. If you turn in your book to page 81, okay, down at the bottom of the page, if you read that example there, they kind of give you a silly kind of scenario. About this professor who's traveling in her old beat up vehicle and the speedometer's broke, but the trip odometer's working. Now it must be some kind of trip odometer because it's giving her distance down to the hundredth of a mile. So it's this old beat up vehicle, but it's got a really fancy odometer evidently. And so she's tracking there at these intervals, these time intervals, and tracking how far she's traveling because she's really worried about speeding. And so if she was really worried, she probably wouldn't get her speedometer fixed. But anyway, you know what I mean? So, but the bottom line is this. We don't have an equation. We don't have a graph, but what we do have is a table, right? And so we've talked about that. So we want to know how fast she's traveling right at 2, which would be the derivative, the slope of that in miles per hour. And so what would be a way we could do it? Think of the quiz question we just went on. What would you do? Use what 2 points? And since we want to give bigger minus smaller, I'll start with that one. And notice it would be D, not D prime I would use, right? Not F, right? The equation here is D. So D of 2.05 and D of 1.95 over 2.05 minus 1.95. Now you might say, why do you take the time to write D of? I think you will find, very quickly in our examples today, that if you will start these problems by writing them in function notation and then go plug in your values, you're much better off, okay? So I always like to start with this. We go back to here. I always like to start writing my slope formula in function notation. Subtract the y's, subtract the x's. Now we can go to the table. What's D of 2.05? 83.54 minus 54. And then Aaron, if you want to calculate that for us. Just do a control divide would be a good start. And then what were the numbers help her out? 83.54 minus 0.54 also, was it? Okay. And then 2.05 minus 1.95 and oops. All right, so 70 miles an hour, approximately. We feel pretty good about it because we picked a point on one side, we picked a point on the other side, right? And we have that. So, very good, and not anything new there if we have a table. All right, now if we turn the page and let's see, we're not going to do that. We're not going to do that. Okay, so if we turn the page past page 81, and we go over to the other page, they work that out for you again there. And then they go on to talk about, on page 82, they talk about a tangent line, and they have a function there. And they graph it, and they say, okay, we could pick some points there. They give you an actual function. If you look at the bottom of page 82, they give you the function x squared plus x. Okay, and so we could pick 2 points really close to 2. If you go over to the other page, they do 2.02, 2.01, and 2. We could use 2.01 and 1.99 if you rather, right? And we would plug those into that function to get the y values, and we would do our slope calculation. So We did it with kind of a real life problem in miles and hours where we had a table of values. If we have an equation, again, like we had an equation on that quiz question, you plug those values in, okay? You could even define the function on your calculator and do that. But again, it's the same thing. It's just doing those calculations. All right, so now, if you turn to page 84, now we're going to look at the professor's situation again. And this time, if you look in the second paragraph, they give you an equation for the D function. They give you an equation for the D function instead of a table. And how could we find the derivative at 2, exactly at 2, without just estimating, right? So on your homework, you're going to do some of this estimating, some of this zooming numerically. You're going to have an equation. You're going to plug in points really close to 2 and do a slope, okay? So that'll be some of what we do. But here's the new thing we want to do. So if you, on your calculators, if you would take a look at that document that I sent you. So this estimating the slope of the tangent line. So if you're not on it already, if you go to the home screen and probably just go to current, it should pop up. Or if you go to the home screen and go to My Documents and then find it under there. Okay? And it was called Estimating Slope, Estimate Slope of a Tangent Line, or Estimate Slope of a Tangent Line. Okay? So go ahead and pull that up. And then, Aaron, if you would go hit Control and the right arrow and take us to the next page. It says in the diagram of the next page, we're going to have a secant line. We got a function x squared, and we're going to look at the secant line, which means it touches in 2 places. So if you go to the next page, okay, so we have a secant line right there. Now see if you can hover your cursor over the Q, and then press down, now you're on the Q, so get a little closer, get that fist, go down a little bit. It's tricky, it is, there you go. Now press down and hold in the middle of the trackpad until you get, there you go. And now you can lift your finger off, and now you can just kind of move in the middle of the trackpad and move it down towards the point P. Okay, just slowly, that's good. Now what's happening to the slope of that line? It's getting less, right? It's a positive slope, go ahead and keep going. And again, it is, it's working pretty good, okay? But we're getting closer and closer to getting the actual tangent line at 1, right? So we could stop along the way. So go ahead and stop right there. And go hit Control right arrow. I'm not quite sure what comes next here. Okay, here we go. This is good. So go up and grab that point again. Go ahead and grab that point, just like you did a minute ago. Is it closing? It's not closing. There you go. Okay, and let's drag that down and get about halfway here. Get down here in the middle a little bit. And we can see the slope. Okay, now we can actually see the slope happening. Now what we're going to, and you guys can be doing this on yours if you want. Okay, stop right there. Okay, now what I want you to do is hit Control period, or decimal point, I guess, period, decimal point, okay? And notice how that says capture. Okay, now I want you to move it down a little more, getting closer to point P. And everybody else can be doing this too. Move it a little closer, okay? And hit Control period again, or Control decimal point, okay? And then move it down some more. And let's keep repeating that process as we get closer and closer. And then when we get really close, we want to just really go in some small increments. Now what we're doing with that Control decimal point, you'll see on the next page we're going to have a spreadsheet. And every time we hit Control decimal point, it's capturing this X and Y coordinate and putting it into the spreadsheet. Okay, go ahead and keep going. Yeah, get down there and then hit, especially when we get close, we'll try to hit Control decimal point a number of times as we get closer and closer. And it's just, okay, that's good. Okay, that's fine right there. So hit Control right arrow and go to the next page. And what we see are some of those points that we have captured there. So what I want to do is, if you arrow over to, arrow over to right there. And what we want to do is hit the equal sign. And what I want to do is calculate that slope. Now, between that point, I want to do it between this point and the point 1, 1, which was the point P. So hit Control Divide for our divide sign, and we're going to do our slope calculation. And so what we want to do is we want to do B1. This is the Y value. So type B1. It can be, I think it can be lowercase or uppercase. I don't think it matters. So B1 minus 1, right? Because our Y value is this is the Y value of that point Q, and then 1 was the Y value of point P. And then on the bottom, we want to do A1. This is the X value of the Q point minus 1. And hit equals. Or enter, I mean, not equals, I'm sorry. And there was a slope. Remember, it was up there about 3 something. Okay, now arrow back up to this point. And then we want to go to our menu. And data, I think. And fill. Enter. And now arrow down. And keep arrowing down. And what this should do is, oops, that's enough. And hit enter. And that should fill that formula down. Now, if you hit your down arrow, okay, so if you look at the formula, see the formula down here? So it's B3 minus 1 over A3 minus 1, and then keep going. And we can see what's happening. That slope is getting less and less, right? And we're not really in there. I mean, and we could put, so let's arrow over here to the A column. And let's actually put in, okay, in number 7 here for yours, let's put in 1.0001. Okay. That's good. Hit enter. That's fine. Hit OK. I think. Oh.
Hit Control 1, 2.
That was bad. Control Z. Okay, delete that, forget it. Okay, but because we can do it on the home screen, all I was going to do is do a numerical zoom here, right? So there's no great thing here. But I did want to show you how we could take a spreadsheet, we could grab these points, and we could get closer and closer, let Q get closer and closer to P. Just another way of seeing stuff we've already talked about, right? We're letting the 2 points get really, really close together and become basically 1 point to estimate the tangent line. And we can see that this will be getting closer and closer to whatever that slope is right at that tangent line. Okay, so just a lot of different ways of seeing this thing we've already been talking about. Okay, hit Control right arrow. I don't know if there's another page here. Okay, so they've got f1 of x at this. Okay, so this is what we want to do. So set up expression will yield the proxy. So we want to do a zoom in. So let's do Control Divide. Put your cursor. Get your cursor down here. I think if you tab or click down there, it's a split screen is what we got going. So there you go. So you want to click down there so you get your cursor down there. So Control Divide, get us a fraction. And so we've defined the function as f1. So let's do an f1 of, so f1 parentheses 1.001 minus f1 of 0.999, right? That'd be on, that way it's on both sides. Okay, and then down below put 1.01 minus 0.99. So again, this is that numerical zooming. We're doing 2 points really close. Should give us an approximate value. Hit enter, and it looks like 2. Now we expected an approximate answer, and we get this. Well, it turns out that is the slope at that point, and to like 3 decimal places, it rounds to actually 2, and so that's what they get. So that's what they put. Okay. All right. So nothing really new there other than we can see this that's happening. Okay, thank you. Well, I'll keep you there as a presenter just in case. All right. So what I would like you to do is in your notes, draw yourself something like this. What we want to do is mimic what we just saw there. Except now we're going to do it for just some general function F and some generic point A instead of 1 or 2 or whatever. Okay? So here I've got a function F, I've got a point A, and what I'm looking for is the slope of that line right there. Now, it's already been calculated for us, okay, right there. So we know that's the slope of the tangent line. But I want to recreate this. What I'm trying to do is come up with some formula here that we can use instead of just having to always do this slope calculation with all these decimals. Can we see a pattern of something happening here? So I'm going to create myself a second point. So I'm going to move over h units. Now, could I pick a point on either side? Sure. When you're doing a zooming, it's a nice thing to do. You're going to be more accurate if you pick one on either side. But we're going to get so close. We're going to let those 2 points get so close that it's not really going to matter. And to be honest, the formula is easier if we don't pick points on both sides. If we just pick A and then a point to the right. It's just easier. So that's what we're going to do. So I'm going to move over h units. So I could call that point B, right? But you're going to see it's going to be easier to call it A plus H. Okay? So I'm going to move over h units, and I'm going to create my second point here, which of course would be f of A plus H. Right? And so we have f of A, we have f of A plus H. And now I want to do the slope of that green line, and of course it's too much. It's too steep, right? It's steeper than the line we're looking for, which is the black line. So I need to do what? How do I turn the green line into the black line? Get it closer together, right? We're saying the same stuff over and over again, right? I just need to get point Q closer to point P, so like Erin did, where she drug it. Now, but we're actually going to think of it a little different. How do I get this point closer to this point? Let H do what? What happens to H as that green X value gets closer to the blue? H is getting smaller, right? As a matter of fact, if H is 0, then they become the same. Of course, that's a problem, right? Because then we don't have 2 points anymore. We only have 1, right? So we don't want to let H equal 0. We want to let H get closer and closer to 0. So this is the advantage of using H here. Instead of calling this point B and say let B get closer to A, we can say let H get closer and closer to 0. Because as H gets closer and closer to 0, H is this distance in between here. As H gets smaller and smaller and smaller, right, the 2 points get closer and closer and closer. Okay, I can hit this button here that says let H approach 0. And so look what happens. That green line eventually becomes the black line. Well, when would it become the black line? Right when H is 0. Of course, we know we can't let that happen because then we can't do our slope calculation anymore because we don't have 2 points. Okay, so what we really want is to let H get closer and closer to 0. And now look at our slope. Our green slope is getting closer and closer to our black slope, the slope we're looking for. Okay, so no big deal here. I mean, as far as we knew all this on the first day of class, right? We get that. Let the 2 points get really close. We're going to get a close approximation of the slope of the black line. But now what we're going to do that we haven't done is we're going to write this out with some notation. Okay, so let's write out the slope of the green line. And we'll use, what the heck, let's use green to do it. Oops, why didn't I get green? Oh, thank you. Is that green? That looks green. That's green. All right, so let's write out the slope of that green line. And we want to use our function notation to do it. So here are our 2 y values, right? So we want to write f of A plus H minus f of A all over, and here's our 2 x values down here, A plus H minus A. Now what's that going to be? That's just going to simplify to H, right? That's just going to simplify to H. Rise over run. Our run is just going to be H, because it's between A and A plus H. Now, I want you to compare that to what we had written in our notes just a minute ago. We had written f of B minus f of A over B minus A. Now, aren't those the two the same thing? Right? They're exactly the same thing. This is exactly the same as this. Now, some people would argue, well, why do we have to do this? Why can't we just do this? This is easier. Well, kind of. It's kind of easier. It's got an A and a B. That's a problem. This has an A and an H. So you say, what's the big advantage? Plus, this looks more complicated. F of A plus H looks more complicated. But it's going to be better. You're going to see it's going to be better to have this one. Now, there are times that we may see it written like this. Okay, in this formula we're going to come up to. This is the one we want. Okay, so you're going to get to know this formula very, very well. All right, now, all that is the difference quotient. All that is right now is the slope between 2 points, A and A plus H. Right? That's all that is. But here is going to be the secret. LIM stands for limit. What we are going to do to this is we are going to, this is the notation we're going to use. We said, what do we want to happen? We want the 2 points to become 1. The problem is we can't do slope with 1. So we're not going to let it actually become 1 point, but get closer and closer and closer. That's what a limit is. You're going to get closer and closer and closer. What are we going to let get closer and closer? We're going to let H approach 0. And that's how we write it right there. We write LIM, and then below that, we wrote H arrow 0. The limit of that as H is approaching 0. So that's what the spreadsheet was showing. If we could have kept going in that spreadsheet, we could have been seeing those slopes get closer and closer and closer because our X and Y's were getting closer and closer to the point 1, 1. The 2 points were becoming 1. The limit as H approaches 0. So it's what those numbers are getting close to. They're getting closer and closer to some number. That is the slope at that point. Okay, this formula is really an important formula. As a matter of fact, let me get out of here right now, and let's go into here, and let's just write that back here. So right here, we're going to write limit as H approaches 0. Oh, shoot. Sorry. F prime of A equals the limit as H approaches 0 of F of A plus H minus F of A all over H. That is a big deal right there. That is the definition, or sometimes called the limit definition of the derivative. The formal definition of the derivative. But what really is it? I always like to think of it as made up of 2 parts. The definition of the derivative. We already know an informal definition. If I would have told you before today, if I just started class today and said, define the derivative for me, what would you have said? Slope. Slope of the function. Keep going. At a instantaneous, at a certain point. Or you might have said instantaneous rate of change. But the key to both of those is it's at a single point, right? That's the definition of derivative, is a slope at a single point. So up until today, that was our definition, right? Kind of an informal definition, but it's the slope or the instantaneous rate of change at a specific point. Well, I would submit to you that that's all this is saying, but just in mathematical language. Look at the 2 parts. Let me underline them here in red. There's 2 parts to this right there. This part is just what? Slope, because it's subtracting the y's and subtracting the x's, right? It's just rise over run, right? Isn't that where that came from? Yeah, that's all it was. It was. So this is slope between this part. Slope between 2 points. What are the 2 points? Slope between what 2 points? A and A plus H, right? So that difference quotient right here is the slope between 2 points, A and A plus H. What does this part do? What's this part do? Let's H go to 0. What's that do to the 2 points? Lets them become 1. Right? Gets them very, very close. So close that we could essentially say they become 1. And what did we say the definition of derivative was? Slope at 1 point, right? So why is this the slope at 1 point? Because it's a slope between 2 points, and then this part lets the 2 points become 1. Sort of. Okay? Closer and closer and closer. That's why this is the slope at 1 point. Because this part is a slope between 2 points, and this part, which is the key, this is what changes it from average rate of change to instantaneous rate of change. This part, the limit, takes it from 2 points to 1, because the H gets smaller and smaller.
Can H be negative?
No. And because that's why we're going to define, we're just defining H as positive, and A plus H, so A plus H is going to be to the right of A. If we want it to be left of A, it'd be A minus H.
Okay.
Now, I can show you that. This is called, so we were, in our example earlier, we had Aaron type it in. We did a point on both sides, right? What would that formula look like? Well, now your 2 points, instead of A and A plus H, they would be A minus H and A plus H. You see how that would be a more complicated formula? It would be this right here. It would be this formula right here. We call it the symmetric difference quotient. So it would be F of A plus H minus F of A minus H, and then it would be all over 2H, right? Because your run now would be H and H. It'd be 2H. And that works, and that's fine. If we get into problems where you have a table, or they just say estimate, sometimes on some of your homework they're going to say, let H be 0.0001, right? And they'll say, find a slope at 2. Estimate the slope at 2. So fine, go 0.001 on one side, go 0.001 on the other side, like we've been doing, and do that. That's fine. On some of the problems, they're going to have you do that. So that's just what we've been doing. Slope between 2 points, 2 really close points. Okay? But on some of the homework, we're going to have, whoops, that was bad. I need to do that. Okay? So we're going to typically, because it just makes the formula easier, we want to do the slope at A. We'll pick A, we'll pick a point to the right, and we'll let the two get closer and closer together. And then I guess I should put that up here. I don't actually have it. Let me put it back up. So there it is right there. Okay? Limit. Oh. Okay? We're supposed to move those things around. But the limit as H approaches 0 of F of A plus H. So it looks real fancy and confusing, but if you just think of it as 2 parts, this is slope between 2 points, A and A plus H, and then this lets the 2 points become 1, basically, by letting the H get really small. And there you go. You got slope at 1 point. Now, how can we use that? Right? That's where what we're really interested in is how can we use that. So that's what we're going to do next. This is probably the hardest part of it. So anyway, I had this drawn up here, but I don't know why. It's basically what we just saw there, right? But I had a nicer way to show you, so that's good. All right, so let's practice this. Let's practice what we're going to need. Now, first of all, we've got to do a little practice just with function notation, okay? So if I give you, you don't have to, you can write this down if you want, not a big deal here, but this is just function notation practice real quick. So if I give you this and ask you for f of 3, what's that mean? Plug a 3. So 3 cubed minus 2 times 3. You probably wouldn't write that out, right? You would just do it in your head. And 3 cubed is 27 minus 6, 21. Right, we know that. But writing it out kind of helps us for the next one. If I tell you this is f of x and I say, what's f of a? You plug an a in. And that's all you can do. Right? And if I said, what's f of German short hair? It's German short hair cubed minus 2.
So it's a 3-dimensional
forget.
German short hair.
Yeah. Yeah, right. German short hair, German short hair. I don't even know what that would look like. Okay, so, and that's where we would stop. In other words, f of something, means take that something and put it in for the input of the function definition. Here's the function definition saying f of x is x cubed minus 2x. F of something is the something cubed minus 2 times something. Now, we can see where we might want f of a, because we just got done talking about this derivative definition that has an f of a in it, right? So we might want to have an f of a, be able to do that. And what's f of 2 plus h? Now, you actually had, you might not remember it, in one of the appendix problems, you had, way back, first couple days, we had some problems like this where we had to do this kind of thing. But it also looks like we're going to have a function notation with a something plus h inside of it, and we're going to have to do something with that. And sure enough, we are. So in this problem, what would f of 2 plus h be? 2 plus h cubed, right? That's what that would be. So if this is f of x, and we ask what is f of 2 plus h, then what we're saying is take 2 plus h, and plug that into the function for x. Okay? And so that's what we'd have. Now, probably going to want to simplify that then. Probably want to cube that out. There will be some of that today. Now, let's talk about that. How do I do 2 plus h cubed? Put it in your calculator. Okay? Now, you laugh, but Aaron, that's the first thing I heard. Let's go to your calculator screen, just hit your scratch pad, and let's type in parentheses 2 plus h to the third power. Hit enter. Oh, that's disappointing.
Control enter.
That's disappointing.
Oh,
Control
so
enter. Try that.
It flips it.
I'll put a decimal point behind the 2, but other than that, okay. Go to menu. Go to algebra. See anything in there?
Expand.
Aha, expand.
Yeah.
Arrow up and just grab it, or type it in again. You didn't need another set of parentheses there, because that parenthesis you have now is the expand, right?
What the
You
heck?
don't want to cube that. There you go. Enter. There we go. Now, I wouldn't get too excited about that, because chances are the question where you have to do this is going to be on the note calculator. Okay? So, in your homework, it would really be a good idea to practice doing this without your calculator. Okay? So, let's talk about it. Well, it's not hard. One way is to just do 2 plus h times 2 plus h times 2 plus h. Now, if you took this as Payne's class, I know you think you talked about Pascal's triangle.
Yes.
I'm not sure in the other advanced maths if they always get to that or not. So, but if you did, fine. This is about the only time we'll use it, you know, so if you got it. And so one way to do it is to just multiply this out. So that'd be 4 plus 2h would be 4h plus h squared. And then we're going to times that by 2 plus h. So now what we have to do is take everything in this one times everything in the other one. So 4 times 2 is 8. 4 times h is 4h. 4h times 2 is 8h. 4h times h is 4h squared. H squared times 2 is 2h squared. And h squared times h is h cubed. And so if you write it in order, you got h cubed, 2h squared, 4h squared is 6h squared. 8h and 4h is 12h plus 8. And so you can get it just fine. Now, Pascal's triangle, you seen this?
Yeah.
If you haven't,
Pain.
you can kind of get the
We used to have
idea. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 1 is 3, 3 plus 1 is 4, 3 plus 3 makes 6, right? And you keep going. Now, there's a lot of cool things about Pascal's triangle, but one of the things it's good for is binomial expansion, and that's what we have here, binomial expansion, 2 plus h raised to a power, or x plus y raised to a power. And so if you look at this, the top row is 2 plus h to the 0, which is 1. The next one is the coefficients on 2 plus h to the first. That is, it would be 1 times 2 and 1 times h. And sure enough, the 1 and the 1. Okay? The next row is 2 plus h to the second, the 1, 2, 1. So that would mean it is 1 times 2 squared plus 2 times the inner product, which is 2h, plus 1 times the h squared. And so that'd be 4 plus 4h plus h squared, which, right? So, look, here, okay, here's the Pascal's numbers, the 1, 2, and the 1. Okay, where did these numbers come from? These numbers came from, here's what you do on the expansion. When it's a power, you take the first term is going to be this one squared without the other one. The next term is going to be this one to the first power, and then this one to the first power. And then the last one is going to be, you won't have this one at all, and then you have this one to the second power, whatever the power is. I'll show you that. Let me get a new sheet. So if I had x plus y, let's just do that. That's a little easier to see, to the third. Here's how Pascal's triangle could help. Now, you're probably already saying to yourself, oh, this is dumb, I'm just going to multiply together. And I would agree, possibly.
I would agree.
If you had x plus y to the seventh, which we won't be getting into, then Pascal's triangle could be a lot simpler. But if you're only going to about the third, probably not that big a deal. But it is kind of interesting. So let's do it. So if we had x plus y to the third, we'd be on this row right here. So what this says is your expansion is going to be 1, which comes from there. And then it's going to be the first thing to the third, and none of the other thing. You could write y to the 0 if you want. Then the next one's going to be the 3, and then it's going to be x to the second, and y to the first. The next one's going to be the 3, and then x to the first, y to the second. And then the last one's going to be the 1, and then no x's, and then y to the third. So in our example, 2 plus h cubed, it'll be 1 times 2 cubed, no h's, and then 3 times 2 squared times an h, plus the 3 from Pascal's triangle, and then 2 to the first, h to the second, and then finally the 1 from Pascal's, and then h to the third. So if you look at this, there's an 8. This would be 4 times 3, which is 12h. This would be 3 times 2, which is 6h squared. And then that would be h cubed. And if you look at the answer we had, it is that. Okay? So that Pascal's triangle can give you the coefficients on that expansion, and then the terms in the binomial go in order of the power. You can see the 2 went from third to the second to the first, and then to the 0. And then the other one, the other term in the expansion goes a reversal. That's a binomial expansion. Okay? We're going to be doing some of that, but again, I think the highest one we will do will probably be third power. I don't want to lie to you, maybe a fourth, but that would be the highest. Okay? But third we will do. So if you'd rather just multiply it out up here like this, perfectly fine. Okay? Perfectly fine. So anyway, so we would have that, and then we would have -4 and -2h, so we'd want to simplify it. Okay, let's look at that in action as an actual derivative. So back to the professor's situation. And so we've got this function right here. Now this is worked out for you on page 84, but it might be best if you don't look at it right now. Okay? And we're going to do this situation. So we've got her distance equation in miles, and we want to know how fast she's traveling right at 2 hours. So we want d prime of 2. Okay? So we already know how we would have done it before today. We would have taken 2.001 and 1.999, and we would have plugged those into that function, and we would have got an estimate. We did it already. We got 7, right? Because we picked really close numbers, and it came out 70, okay? But now let's use this new thing, because this new thing is more exact, okay? This new thing is not saying get this close. It's saying get infinitely close, because it's saying let h go to 0. So here we go. D prime, according to our new formula, okay? So now instead of f in our formula, we've got d. And instead of a, we've got, no.
T, D prime.
No, what's a?
T.
2. Okay?
Oh.
Right here? Right here? Right here? We're finding d prime of 2. So this is our formula. Okay, so we talk about the derivative formula right now. We're talking about this. So if we're going to do d prime of 2, this will be d, this will be D, this will be D, and the A, everywhere we see an A, that will be a 2. So that'll be a 2, that'll be a 2, and the H is still going to be in there, right? There'll be just an H in there, right? All right, our H is the thing that's getting small. So when we were doing our zooming, our H was like our 0.001, that kind of thing. We were letting H get small. Okay? Now we're not going to pick a particular H. We're going to do this, write out this limit thing. Okay, so here we go. So, limit. So I'm just copying down the formula now. Limit as H approaches 0. Got my difference quotient. So what do we say I'm going to write here? How much?
2 plus H.
Yeah, 2 plus H, but you're forgetting something. D of 2 plus H minus, right? We said where in your formula where the F was, is in our function now it's not F, it's D, minus D of 2 all over H. Now, we're going to do this without our calculator, because you're right now, calculators are wonderful things. We could define our D function as this. We could actually type this in just like this. There's actually a limit command. There, we could define D as this. We could type this in. It would just tell us the answer. That's not a value to me because I can train my, well, I used to always say my daughter when she was in like 4th grade. I could say I could train my 4th grade daughter to just, she's a junior now, so it's not that big a deal of saying, she's about the same age as you guys, so it's not that big a deal. So, but I could train any old 4th or 5th grader to come in here, type that in the calculator. What would they know? They wouldn't know anything. So, I want you to be able to work this out, right? Now, if you want to check it, obviously you can check it on the calculator. That's fine. So, that's our first line. The second line is going to be, copy that down.
Yes, sir.
Okay. Now, I want to take these two things in the blue and work those out. Okay? So, what's D of 2 plus H? We just practiced that. Take 2 plus H and plug it into here for T, right? What's D of 1? Put a 1 in for T. What's D of 2? Put a 2 in for T. What's D of 2 plus H? Put a 2 plus H in for T, right? Like the German shorthand, right? So we're going to take 2 plus H and put it in here for T. So we're going to have 10 times 2 plus H minus 15 times 2 plus H squared, correct? So that's the first box. That's the D of 2 plus H. So for those of you that when we were doing these graphs and stuff in last chapter said, when are we going to get to some real algebra? Right? Some of you were saying that, I know. You won't admit it, but you were, right? Well, good. You're here. You get to do this algebra. All right. Minus D of 2. What's D of 2? This we can just do in our head, or you could use your calculator now, it's fine. But 10 times 2 is 20. 2 squared is 4 times 15 is 60. 20 plus 60, 80. Right? And then we got an H on the bottom. So the D of 2 plus H gave me that part. The D of 2 gave me the 80. Right? And now I got this. And now it's a bunch of algebra. So the next line, now don't forget, I think you want to be really neat with your work here. I can promise you on the next quiz, which will be next week sometime, early next week, next quiz, you're going to have this that you're going to go through. Maybe a couple of times. Maybe a couple of times. Okay? So get good at showing your work here, taking your time, right? Making this work out. All right, so here we go. So let's take a little bit at a time. So this is going to be what? 20 plus 10H. Now, I might go off to the side to do this part. I guess I could show it here, but I think I'm going to FOIL out this 2 plus H. So what is that? 4 plus 4H plus H squared. Don't forget that that's FOIL. We do not distribute a power. This is not 2 squared and H squared, right? Do not make that mistake. Okay, this is a FOIL. This is a multiply it out. So it's 4 plus 4H plus H squared. And then we have to multiply it by negative 15. Yes. Thank you. That would have been bad. Right here, 10t plus 15t squared. Right there should be a plus.
So is mine.
Good catch. Okay, this minus is that minus right there. But that is the function. Okay, so that's a plus. Good. So now it's, okay, so it's now plus 15 times this. So 60 plus 60h plus 15h squared, and then minus 80. So when you're doing these problems, if they get kind of messy, you're on the right track. Okay? So now what? Simplify. 20 and 60 is 80. Minus 80. That should happen. That should happen. If we don't get some things to cancel, something's wrong. That should happen. Okay, so let's go ahead and simplify the rest. So what do we get? 15h squared. We would probably write it in that order. I agree. 15h squared plus 70h divided by h. Now, before I keep going, it's really easy to get lost in the trees here a little bit. Lost in the weeds and not be able to remember what we're doing. So I'm going to stop right now and just remind myself, what am I even doing here? Oh, wait a minute. We had a d function, which was miles. We're trying to find the miles per hour, the slope. We use this new formula, which really is just slope, right? It's just slope between these 2 points, 2 and 2 plus h. We're letting h go to 0, which means we're letting the 2 points get really close to 1, right, as h goes to 0. So we're doing all the algebra to this with our equation, and so that's what we're caught in the middle of right now, is doing some algebra. So now we get down to here. What algebra can I do to this? Can I factor out an h? Or, now you're right, there's two ways to think about this. I can, and I like what Matthew's saying here, is we can take this divided by h, and we can take this divided by h, divide both of them by h, and an h would cancel. Or we could say factor out an h, and cancel an h, right? I'm going to show it that way, but I like both ways. So I'm going to show it as factoring out an h, and we get 15h plus 70, because sometimes when we cancel, we do some goofy things we're not supposed to. I'm going to show it like that, but it would have been possible to just know, hey, we're going to divide each of those by h, and we would just end up with 15h plus 70. Now, I'm out of room. It should really go down here, but I'm going to go off to the side here. So I've got limit as h goes to 0 of 15h plus 70. Now, I'm not done, but I'm going to circle that here. So now let's think about this a minute. So as h gets really, really small, tell me what's going to happen to this. Isn't this going to get closer and closer to 70? Because 15 times a really small number is going to just keep getting smaller and smaller and smaller, right? And so we said you can't really let h equal 0 because then the 2 points become 1. But here's where we could probably violate that a little bit. Because we can say to ourselves, okay, if we let h go to 0 here, get smaller and smaller and smaller, this is going to be 70 plus some small amount. As h gets closer and closer to 0, it's getting closer and closer to 70, but can it ever go below 70? It can never go below 70. 70 is the limit, right? So when we get down to here, it actually is okay then to take a 0 and plug it in at this point for h and know that our answer is actually 70. So before, when we were putting in two really close numbers and we were getting 70, it just worked out nice that we were getting, we zoomed in close enough that our estimate was actually the exact answer. But here we can see without a shadow of a doubt that the limit actually is exactly 70. That is going to get closer and closer and closer to 70. So that if we could let the 2 points become 1, the slope right at 2 would be exactly 7. No estimate, exactly 7. Okay? Now, notice, not until we got to here could we put a 0 in for h. What if we'd have tried to put a 0 in for h up here? We'd have been dividing by 0. Dividing by 0, dividing by 0. So it was never okay to plug a 0 in for h here because our slope formula would have made no sense, which of course we know. you can't do slope at one point. There'd be no run. You'd be dividing by 0. But the algebra works out and allows us to cancel that h, which then now we can put the 0 in for h. And that's what's going to happen. Okay, let's take a look at this one now. So now different problem, but this is just more practical. So the question here, so the question on that one was, here is Professor X's distance equation. Find her velocity at 2 out, which we know means the slope at 2. The question on this one would be, here's the function f. Find the slope of the tangent line at 2. Same question, right? Same question. Both of those are find f prime at 2. Well, we now have a new formula for finding f prime at a point. We do the limit as h approaches 0. Tell me what to write. I should have picked something besides 2. You're going to think it's 2 all the time. This 2 comes from there, right?
Yep.
We're putting a 2 where the a was in our formula. F of 2 plus h minus f of 2 all over. Now notice we're finding f prime, but in our formula we use f, right? Because we're finding the slope of f, and that difference quotient is the slope. So we need the slope of f, so it's got to be f in there, okay? F of, we're not going to have time to finish, but the blue parts, right? So here I got limit as h goes to 0, but so f of 2 plus h, what do I got? What do I do? You put 2 plus h into the function f. So we're going to put a 2 plus h there. So it's going to be 2 plus h squared plus 2 plus h. I'll put parentheses around it, but it doesn't really need it. Then there'll be a minus. And then f of 2. 2 squared plus 2 is 6 all over h. FOIL that out. 4 plus 4h plus h squared plus 2 plus h minus 6. Am I on the right track? I really would encourage you to keep writing the limit as h approaches 0 every time. So you remember, okay, eventually I want h to be 0, but I can't plug a 0 in now because I divide by 0, so that's no good. But a bunch of good things should happen here, right? 4 and 2 is 6. 6 minus 6. Cancel out. So I get the limit as h approaches 0. I have what? H squared plus 5h over h. I can divide both of those, or I can factor out an h. No matter what, I'm going to end up with h plus 5, right? H squared divided by h is h. 5h divided by h is 5. Or factor out an h on top and cancel it. Now we can put a 0 in for h. The answer. And what is that? Don't get lost in the weeds. It's a limit, but what else is it? It's the slope of this parabola at 2. Exactly 2. We didn't have to do an estimate. We didn't have to pick a 0.001 for h and let him get really close. We can actually find the exact slope at 2. Now, eventually, this is going to be called the long way of doing the derivative. We're not going to have to do this all year long. We're going to come up with some shortcuts. We'll come up with some shortcuts. Okay, on that assignment sheet, the 2.1 line is your homework, the 2.1 line. So in there, you're going to be doing some slope between 2 points. You're going to be doing some average rate of change. They're going to have some problems. We're going to say let h be 0.001, which means you'll just get, put a 0.01 in for h. So in this problem, you'd have f of 2.001 minus f of 2. Plug those numbers in, calculate your slope. And then there's going to be some where they're going to say, they probably will say use the limit definition. So, and I always seems like I have somebody do this. Don't go through and do this long method every problem where it says find f prime, because some of them you're just picking close points and stuff. Read the directions. I think it's the ones where they say use the definition or use the limit definition of the derivative to find this. That's when you're going to be doing this long version. Okay? All right. So that's the homework 2.1.
So we don't have to fit the whole time?
Right. Thank you, Eric. Yes.
What's after you guys? So
Sure.
I don't have that. Get it right.
Charge this boy Well, there's a South student night, and there's a South student tomorrow night, and we have. Well, the first